In this technical walkthrough, I'll explain how our malaria detection system was engineered as a full-stack Rust application, with a strong focus on architecture, performance, and efficiency. Everything you'll see, AI training, inference, backend, and frontend, is written entirely in Rust. Architecturally, the system is split into clearly defined components, each with a single responsibility. We have 1. A model training binary. 2. A separate inference server binary. 3. A front-end web application. This separation allows us to train once, deploy many times, and keep inference lightweight and fast. Let's talk about the code structure. The AI model training logic lives in its own Rust binary, completely isolated from the server code. This binary is responsible for dataset loading and preprocessing, model definition using burn, training loops, loss computation, and optimization, serializing trained weights to disk. The Inference server is a different binary. It does not train. It only loads the pre-trained weights, initializes the model in inference mode, exposes an API for predictions. This design ensures faster startup time, lower memory usage, cleaner and more maintainable code. The model itself was trained from scratch using the Burn framework, which is designed for performance and safety in Rust. Training in Rust gives us zero-cost abstractions, predictable memory allocation, no Python interpreter overhead, full control over compute usage. Because Burn is backend agnostic, we can optimize for CPU execution while keeping the model efficient and portable. The result is a model that is fast to train, fast to load, and fast to execute. One key advantage of this approach is low compute utilization during inference. Since the model is compiled to native code, memory safe and allocation efficient, free from runtime garbage collection. Inference runs with low CPU overhead, minimal memory footprint, very low latency. This makes the system suitable for resource-constrained environments, such as clinics with limited hardware. On the front-end side, we used U, a Rust framework that compiles to WebAssembly. U allows us to share data models and types with the backend, catch UI state and logic errors at compile time, avoid common JavaScript runtime issues. From an AI systems perspective, this is powerful because input validation is strict. Data flowing into the model is well-defined. The front end remains stable and predictable. This is especially important in medical and diagnostic applications. Using Rust across the entire stack gives us measurable gains: faster execution, lower compute costs, strong safety guarantees, easier long-term maintenance, a unified language for AI, backend, and frontend. This is not just a technical choice, it's a strategic one. In summary, this project demonstrates how Rust can power efficient production-grade AI systems, from training to deployment, with performance and reliability built in. Thank you.